Hi everyone, my name is Aarun and today I'll be presenting my paper titled Risk-Sensitive Reinforcement Learning for Designing Robust, Low-Thrust Interplanetary Trajectories. So the motivation for my paper is that as of now, small sats are increasingly being proposed for interplanetary missions, largely because they can be built both cheaply and quickly while still being able to perform tasks similar to those of larger spacecraft. However, since they're developed on such tight budgets and short timelines, they're often built with components that lack reliability, making them prone to various control execution errors, such as those resulting from misthrust events, actuator noise, and misaligned thrusters. And so, if we want to reliably utilize small sats in deep space, then we need to be able to handle all of these issues on the fly, and this motivates the need to design robust trajectories. Reinforcement learning, a subfield of machine learning in which an agent learns by interacting with its environment via trial and error, as opposed to from a fixed data set, has recently shown promise in generating such trajectories. However, most existing approaches assume that the types of control errors and their associated magnitudes are known ahead of time. Unfortunately, space is inherently unpredictable, and so we often don't know what kinds of errors the spacecraft will encounter once launched, and without having any prior knowledge, we're just left hoping that the trajectories designed using RL will generalize to unseen errors, which oftentimes they don't. And so to address this, I'm proposing using risk-sensitive reinforcement learning to design trajectories that are robust to unknown control execution errors. On the right-hand side of this slide is a concept figure illustrating what I expect to see when comparing my RSRL approach with that of traditional RL. Specifically, I expect both methods to succeed in the nominal case, which is free from control execution errors. However, in the perturbed setting where things like misthrust events can occur, I expect RSRL to generalize effectively, whereas traditional RL will not. The specific use case that I'll be evaluating my approach on is performing a time-fixed, minimum fuel, low-thrust transfer from Earth to Mars under three-body dynamics. Specifically in this scenario, the spacecraft will start at Earth and will need to execute a sequence of maneuvers to align its position and velocity with Mars before the simulation ends, all while trying to minimize fuel usage. And so here's a table from my paper outlining the key parameters that are utilized in setting up this scenario. Now, in order to train an RL agent to actually design an Earth-to-Mars transfer trajectory, we need to first reformulate the problem as a Markov decision process, or MDP, which is a mathematical framework utilized to model decision-making problems where an agent, in our case the spacecraft, interacts with its environment to accomplish a goal. An MDP is formally defined using a tuple S, A, P, R, and P naught, where S is a set of states the agent can be in, A is a set of actions the agent can take, P is the transition function, aka the dynamics, R is the reward function, and P naught is the initial state distribution. And so when solving an MDP, the goal is to find an optimal policy. You can think of this as a strategy of sorts that maps states to actions such that the expected return, which is comprised of a discounted summation of rewards obtained from the reward function, is maximized. And so now to actually formulate the Earth to Mars transfer problem as an MDP, we need to first define what S, A, P, R, and P naught are. And so in my paper, I've decided to define them as the following. The state space is just comprised of the positions, velocities, and masses that the spacecraft can achieve at any given time step. The action space is a sphere with radius equal to the maximum delta V the spacecraft can perform during that time step. My transition function is just the three-body equations of motion, and my reward function is defined as this piecewise function, which penalizes the agent at each step based on fuel usage, and at the final time step imposes a large penalty / reward based on the mismatch between the spacecraft's and Mars's final position and velocity. And lastly, the initial state distribution is the initial state of the spacecraft, and that was defined in the table we saw earlier. And so while the previous slide defined the nominal Earth to Mars MDP where absolutely nothing went wrong, this slide shows how that MDP is then modified to create our testing environments, which is done by incorporating control execution errors. And so the first such error that we include is a misthrust event, which is simulated by randomly selecting a time step in the episode and zeroing out the thrust vector at that time. We then allow this misthrust event to continue with probability PMTE at each subsequent step for up to a maximum of n MTE steps. The second control error is actuator noise, which is modeled by adding Gaussian noise to the agent's chosen thrust vector. And lastly, thruster misalignment is introduced by sampling a random unit vector and utilizing it along with the predefined rotation angle to construct a direction cosine matrix that rotates the thrust vector at each time step. And so here's just a table with the parameters utilized to instantiate each of these control execution errors. And so with the training and testing MDPs now defined, we can now apply an off-the-shelf RL algorithm to solve them and establish a baseline for comparison with our RSRL approach. For this baseline, we use proximal policy optimization, or PPO, which is a model-free, policy gradient actor-critic algorithm. At a high level, this just means that PPO doesn't require a model of the environment, as it learns a policy by directly interacting with its environment to collect transitions for approximating its objective, the expected return, which it then maximizes via gradient ascent. It also uses two neural networks, an actor that's in charge of selecting actions, and a critic that evaluates them to make more informed decisions about how to go about updating its policy. Also, another thing to note about PPO is that it limits just how much its policy can be changed each update using the following clipped objective, which helps stabilize learning. And so although optimizing the expected return, which PPO precisely does, has yielded some promising results, it often leads to policies that are sensitive to initial conditions, prone to instability, and lack robustness. And this issue stems from the expectation operator in the objective, which tends to overlook rare but significant trajectories. In contrast, RSRL approaches account for these significant trajectories by introducing risk into the standard RL objective, either by introducing risk as a constraint or embedding it explicitly into the objective function, and therefore don't suffer from the same issues plagued by vanilla RL. In this paper, we decided to take the latter, more explicit approach and optimize the exponential criterion, where beta here is a risk parameter whose sign specifies whether we would like this objective to be either risk-seeking and focus on achieving really high rewards, or risk-averse and be more cautious and make sure that failure is not an option, even if that means we end up sacrificing some optimality along the way. And so for implementing our training and testing environments, we utilized Basilisk to construct the simulation, which included modeling the three-body environment, as well as defining the initial conditions for the spacecraft, Earth, and Mars. We then wrapped this simulation with a gymnasium environment to formalize the rest of the MDP so we could then train our reinforcement learning agents. And for our baseline algorithm, we utilized the PPO implementation from Stable Baselines 3 and extended it to develop our RSRL algorithm, risk-sensitive PPO, or RSPPO, by replacing the standard PPO objective with the risk-sensitive exponential criterion. And so here's the network architecture utilized by both PPO and RSPPO, along with the respective hyperparameters. You can see here that the configurations are nearly identical except for the entropy coefficient C2, which is excluded in RSPPO since the exponential criterion implicitly upper bounds the standard RL objective augmented with an entropy term. And so here are the results from my experiment, which we obtained by first training each algorithm across 5 different seeds for 1,000,000 time steps each, and then sampling 1,000 trajectories from each environment to compute the average metrics that are in this table, as well as build out the histogram plot on the right of this table. And so from them, we can clearly see that RSPPO with a beta value equal to negative 0.005 and beta equal to negative 0.001 consistently outperforms PPO in terms of position and velocity constraint violations, as well as overall return in the nominal case. Moreover, in the presence of control execution errors, RSPPO with those beta values shows significantly smaller increases in constraint violations compared to PPO. In fact, across all scenarios, RSPPO maintains position violations at or below roughly 1%, while PPO's position violations are much higher. Interestingly, RSPPO with the small positive risk parameter also surpasses PPO in every setting except the nominal case. This is somewhat counterintuitive, as risk-seeking policies are not typically associated with being robust to changes in dynamics. However, it is possible that the added risk promotes broader exploration during training, enabling the agent to learn behaviors applicable to a wider range of states that PPO may only encounter once errors arise. And so these findings suggest that incorporating risk, whether risk-averse or mildly risk-seeking, can enhance policy robustness. At the same time, setting beta too high or too low, for example, beta equal to negative 0.001 or beta equal to 0.01, leads to degraded performance across all metrics relative to PPO. And this is expected, as excessive risk aversion can hinder exploration and prevent the discovery of optimal strategies, while overtly risk-seeking behavior can produce reckless actions that may yield large negative rewards. And so we can see the advantages of the RSRL approach more clearly by visualizing the trajectories obtained from both PPO and RSPPO. From this plot, we can see that the trajectories designed using PPO in the nominal case, represented by the color blue, end up very close to Mars, but under the presence of control execution errors, end up spreading out more and more. In contrast, RSPPO with our best beta parameter, -0.005, designs trajectories that reach Mars regardless of whether there are or are not any control execution errors, as demonstrated by all of the trajectories being much closer to one another and in the proximity of Mars. And so, although I've demonstrated that RSRL can design quite robust policies, I recognize that no policy is universally robust, which means that some form of retraining or adaptation will always be necessary if this solution ever gets deployed on board any real spacecraft. I also selected the beta parameter through trial and error, an approach that obviously isn't very feasible during real missions. So in the near future, I plan on exploring how adaptation can be performed online in a sample-efficient manner using model-based RL methods, as well as thinking about how we can go about learning this beta parameter on the fly. And so here's just a summary slide recapping all the key points that I made in my presentation, and below is also my contact information if you would like to reach out. Thank you.